in this workshop. And today I'm gonna give an overview of my work on 3D shape models of animals for mesh reconstruction. Okay, so why 3D animals? So modeling and capturing animals in 3D has many applications, and of course in entertainment. If we create virtual animals, we can populate VR and AR worlds. And in robotics, we can use 3D for capturing and simulating the fast motion of animals like the cheetah. And in conservation, we can use 3D models for tracking endangered animals, and also for analyzing their behavior in their natural habitat. And then there are many more applications in smart farming, in neuroscience, and so on. So all of these applications, they require to capture 3D shape and pose from images to go from scalable generation of realistic avatars to the automatic interpretation of visual data. And this process of estimating 3D shape and pose of the animals from an image is what we call a mesh reconstruction. So usually this is a model-based approach based on 3D articulated shape models, which are learned from 3D scans. And this is what actually the simple model is. Simple is the most popular tool for doing mesh reconstruction for people, and was introduced in 2015. And in 2017, we introduced the small model that can be considered a sort of animal equivalent of simple, with some differences. So first of all, simple is a single species model for just the human, while small is multi-species. And we can create 3D models for quadrupeds that belong to one of these 5 families highlighted here. So the Hippopotamidae family, the Bovidae, and the Felidae, the Canidae, and Equidae. And another difference with respect to simple is the training set. So simple was learned from thousands of 3D scans of people. And of course, we cannot do the same for animals. We cannot bring wild animals to the lab. So what we did was to use toys. You see like 3 examples on the top right. And this image here shows the 3D scans of all the toys that we have used for learning the small model. And you can see there are not so many. There are actually only 41. And most of them, they belong to the Felidae family. So the lion, the tiger, the cat, and so on. So for training the small model, the first thing we have to do is the registration of the scans. And this means to bring all the scans in a surface correspondence and have all of them represented with the same mesh topology. And here the correspondence is indicated with colors. So for doing registration, we introduce what we call a gloss registration. So we define a part-based synthetic deformable model that we call gloss, and then align the model to all the scans. So here, this video shows the process of aligning gloss to AINA. So we did the same for all the toys, obtaining this surface and the 3D pose of the toy. And then knowing the 3D pose, we can do an unposing of the toys. We can bring all of them in the same reference pose or T-pose. And this is an important step because we want to we want to disentangle the mesh deformations that are due to pose to the ones that are only due to the intrinsic shape of the animals. And then on this post-normalized data set, we can do PCA. So we obtain an average toy that becomes the smaller template and a linear space of deformations. And then changing what we call the shape variables beta, we can generate animals as deformations from the template. Okay, then we can look at how the smaller model shape space look like with this type of visualization. Here we see the first 4 principal components. The thickest arrow indicates the first component, which captures essentially a variation in scale. And then in the vertical arrow indicates the second component that seems to span the shape variation from horses or zebras to lions and so on. So if we take the shape variables for all the toys, this is a high dimensional vector. We can create a 2D visualization of these variables for the training set samples. And we can see that they form clusters based on the family labels. So I think here is also interesting to see that the cats and the dogs, they're similar in this shape space, and they are also close in the family tree. Okay, then we have this linear shape space, and we can generate samples for animals. We can sample the shape variables and obtain random animals. But given we have this common shape space over all the families, what we obtain are animals that are like a mixture of different species. And these animals, of course, they don't exist in nature. So what we should do is instead to sample the families. So we can compute what is the average shape variable for each family and the covariance matrix. And then we should sample these multivariate Gaussians. If we do this, then we can actually create samples that are characteristic for each family. Here, the colored meshes are the average animal for each of the family considered. So once we have the desired shape in T-pose, V-shape, we can articulate the mesh actually using the simple model code. We need to provide the pose variables that are per joint 3D rotations. And we obtain a pose mesh with a linear blend skinning. So differently from the simple model, we don't have pose-dependent deformations. And this can be like a suboptimal for animals that have a strong skin deformation with pose and motion like tigers. So when we align the small model to images for mesh reconstruction, we minimize an energy like the one at the top here. So we have two data term, key point reproduction error and silhouette matching error. And then a set of priors for the camera, joint limits, pose prior, and shape variables prior. And we minimize this energy over the betas, the shape. Theta is a 3D pose, T is the translation, and F is the focal length. And we assume a perspective camera. And so if we look at this lion example here, if you use only key points, we obtain a reasonable, like an animal with reasonable proportions in terms of skeleton. But for capturing the main, we need to use the silhouette. And all the examples here are all obtained using both the key points and the silhouette terms with the manually annotated key points and masks. So what is missing in SMAL? Well, there are hundreds of animals, maybe 1,000 missing, but there are animals that cannot simply be added buying more toys, like the giraffe, because in this case we would need more parts for the neck, and the moose because it has big horns, the elephant because it has a trunk and has these very big articulated ears. But also there are animals that even if they're similar in skeleton to the small animals, they don't exist as toys, and we will never be able to scan them. For example, the northern white rhino, there are only 2 exemplars left, and the Tasmanian tiger, which is extinct. So for the animals that are not too far from from SMAL, but they're not represented, like the rhino, even if we cannot maybe recover the shape from one image, we can try to leverage different images for actually capturing a reasonable 3D shape. And this is because even if we get random images from the web of the same animal, those images, they have different poses, different camera, but what they all have in common is the 3D shape of the animal. So what we can do a joint alignment over all these images, given again 2D key points and silhouettes, so we can minimize this energy. And now we are assuming the shape is the same, so we have a single beta variable and a set of pose variables, one for each image, translation, and focal length variables. So if we do this, we obtain for the rhino the closest approximation to rhinos in the small shape space, which is this sort of big hippo. And of course, this is not sufficient because what characterizes the rhino is the horn. But the smaller shape is a good approximation. So now we can change a little bit the representation of shape and represent the animal shape as the small shape, V shape, plus a set of vertex displacements. And then we can fix the betas, the pose, the focal length, and optimize only over the vertex displacements for improving the fit into the key points and silhouette. And this is this model-free optimization needs to be constrained. So we use as rigid as possible regularization and Laplacian smoothing as regularizers. And we also make the assumption that the body of the animal is symmetric. So, and if the silhouette actually contains the shape detail that we are missing, the horn in this case, then with this optimization, we can improve the mesh reconstruction. And with this better estimation, we can also grab the colors from images and create textured avatars like we did for the rhino. For the Tasmanian tiger, we found online this nice movie from the Hobart Zoo, where they hosted the last exemplar of the Tasmanian tiger in captivity. So we took a few frames from this video and created this the avatar, corresponding avatar. And of course, the video is black and white, so the animal is gray, but the real animal was brown with black stripes. So another interesting animal we work on is a Grevy zebra. So here we collaborated with Wild Book. So Wild Book is an initiative where they use citizen science for counting the Grevy zebra individuals. So the zebras, they are characterized by the pattern of their stripes, which are unique for each animal. They're like a QR code. So in Wild Book, the people can upload the pictures, and then the system automatically matches the images based on the stripes. So we got from Wild Book several pictures of the same individuals, and we created zebras avatars. So here, given the pictures, they can come from different sources. Where there were color casts, we applied some automatic white balancing so that we didn't introduce a natural color transition in the textures. So given these avatars, we can actually do a PCA and see if we have a Grevy zebra shaped space. So now here you can notice that the first component is not scale anymore. This could be that the zebras, they have more like a similar shape, but size, sorry. But in reality, the fact that we don't use calibrated data is a reason. So all the scale variation are accounted by the camera model, the perspective projection camera. So with the avatars, we can sample poses and sample random backgrounds and create a synthetic data set, which is the one here at the top. And at the bottom is a set of real images. And here, so actually the third picture in the synthetic data set is a random picture of a plain zebra. And you can see the difference with the Grevy. So the plain has these thicker stripes down to the belly, while the Grevy has thinner stripes and a white belly. So these are actually the data sets for our 3D Safari paper. The training set, which is completely synthetic, and the test set. So given we know the individuals, the pictures, we pay attention not to have in the test set pictures of zebras that were used for creating the training. So then we train a neural network for mesh reconstruction that also estimates the texture map. So estimating the texture map made it possible to use a photometric loss both at training and at test time. So training together with a strong 3D supervision. So given we only use synthetic data, we know everything about the rendering process. And at test time, we can perform a unsupervised refinement based on the photometric loss. And you see the effect of this refinement here in this example, where blue is the outcome of the feed-forward network, and pink is after the refinement. And in the network, we represent the zebra shape as the average small horse plus as this vertex displacement that here we represent with the network layer. So these are some results. The first column is the input image that is a bounding box with the zebra. Then we have the overlap of the mesh, the reconstructed mesh, and the estimated texture map, and the rendered animal with texture and without texture from a different view. So here the texture map that we predict mostly has an accurate prediction from the camera view. We don't make an assumption of symmetry, and we can also notice that the shading is included in the texture map. But I think in general, the results are quite nice. So why it works? Why using this only this synthetic data set works in this case? I think it's for two reasons. So the Grevy zebra lives mostly in a specific area in Kenya that is indicated here in red. Unfortunately, it's a very, very small area. And this is near the equator. So lighting conditions are always the same, and so our avatars have a realistic shading. And the zebras are quiet animals. They spend most of their time standing, walking, or eating. So a simple 3D pose prior is sufficient to sample poses for the synthetic training set. And this video here, we took this video when we visited the zebras after we submitted the paper. And then we applied per frame reconstruction. So, and I think it's a nice result. So, but there are animals that are a lot more challenging than zebras, like tigers. And in general, all the cats, they have very complex poses. So these are pictures from the Amur Tiger data set. The Amur Tiger is also an endangered species. It's very hard to observe in nature. And this data set is composed by video of frames filmed for animals in captivity. So you can notice complex poses, very strong shadows, camera effects. It would be very hard to create a synthetic training set with the same distribution of this data. To address these problems, complex poses and complex images, what we did was to learn a 3D pose model from animation data. And we also defined a shape model, a new shape model set so that we had the animation skeleton using synthetic deformations. So here you see some samples from the shape of this synthetic shape space and some samples from the pose model that we learned as an autoencoder. And then we train a network using the synthetic 3D shape and pose models as an initialization. And we only use 2D supervision and no bounding boxes. So specifically, the synthetic shape model is generated by this shape predictor. And then we have this vertex displacement on the top that are learned. And the synthetic pose model initializes the pose decoder that we use to predict 3D pose from image features. So these are some examples from the Tiger data set. The first mesh is the synthetic model, and the second mesh is after this refinement with the vertex displacement. So with the refinement, we lose a bit of the details in the synthetic model, but we get better intersection over union score and PCK scores. So then dogs. So dogs are not well represented in SMAL for two main reasons. We have a limited training set. We have only five samples in the Canidae family, and not all of them are dogs. And in the original SMAL model, we don't have articulated ears, so all our animals have ears, pointing ears. But dogs, many breeds, they have floppy ears, and even if the dogs, they don't really move the ears like elephants would do, they can move with motion. So we need to have articulated ears. So to overcome these two limitations, we bought more toys, more dogs toys. And then we register the toys with gloss. And these are the unposed meshes with the segmentation of the gloss model. And you can see that the head now is not completely blue. It's not a single part, but we have these pink and green ears that represent the fact that we have articulated ears. So we can do the PCA on that data and learn a small model for dogs. And now the shape space look like this. Again, the first component is scale. We have small and big dogs. And then the other components mostly represent variations from shepherd-like dogs to mastiff-like dogs that have very different tail, ears, and mouth shape. And now we can sample, create samples from this dog small model. And so every toy is a pure breed animal. But now when we do samples, we obtain animals that are a mixture of different breeds, which is perfectly fine for dogs. So then we took the tiger network. We replaced the tiger model with the small dog model, and we train on the Stanford Extra data set. So these are some of the mesh reconstructions. I think they're nice because they have a reasonable pose, even if seen from other views. And we can capture some breed-specific features like the floppy ears. Yeah, so in conclusion, so according to my experience, using toys was a good idea, and I have to give full credit to Michael for this, for learning 3D models. But we still have to actually evaluate these models using 3D measurements. And there will be a talk from a student, a C, later on this. And the silhouette is informative, but it's not sufficient because you cannot really reconstruct detailed face features from silhouettes. Synthetic data is useful if we don't have access to real data. And we can also transfer some knowledge across species. Like we can, I have used tiger poses for the dogs. So for the moment, we can do that. We'll do something better in the future. So my view for what's next, I think we need to learn more from real animals. And even if we cannot bring big animals in the lab, so maybe at Tübingen they can host the elephant in their super big lab. But in general, maybe we can capture on partial body scans for animals, at least for domestic animals. We can capture probably depth information, then smoke up and video and multi-view images. I think we need to try to, you know, to get more data and probably more modalities together. And we are working on this. And we need more real data with 3D information for evaluating 3D animal models, but also for a proper evaluation of mesh reconstruction methods. So often we evaluate 3D reconstruction using 2D, using PCK and intersection over union. And this is not, in my view, a good way for evaluating mesh reconstruction methods. And last, I think we should incorporate top-down semantic knowledge during training to learn models that can better interpret visual data. And we also, hopefully, we will have a paper on this soon. So I would like to conclude with a thank you to you for your attention and to my co-authors, and especially to Seyhan and Marcus for scanning the toys.
Thanks a lot, Sylvia. Amazing talk.
You
summarized your results as being quite nice. I would say they're excellent, really outstanding work, also technically deep. Yeah, we do have a bit of time for questions. Raise your hand for an in-person question. I see Himal has his hands up or her hand up already. Yeah, that's great to see. So, and another thing I would encourage you, if you have a poster later on in the session, then also make a comment in the chat. I'm working on something similar, paper ID 55. Don't overdo it and spam the chat, but we can have a few references here to facilitate, yeah, a connection to your own presentations. But first of all, yeah, let's have a bit of time on Sylvia's talk. Himo, do you want to take the stage and ask a question?
Hi, can you hear me?
Yeah, we can hear you, not see you, but that's fine.
Perfect. No, my Zoom is about to crash probably. Yeah, Sylvia, great talk. I wanted to ask, I think your methods are directly applicable to some problems in camera.
Sorry, I couldn't hear.
Unfortunately, your last
he
word was
warned
cut.
that it was gonna, his Zoom was gonna die, and then it died.
Yeah, it's back. It's back.
Okay,
It's
good,
back.
good.
Yes. Hi, Sylvia, great talk. Thanks. I was wondering that if you know about camera traps, that is a wealth of data available through camera traps. And I believe your methods are pretty much applicable in that scope, within the scope of what biologists would like to learn, especially in camera traps usually are primarily done to, let's say, do a evaluation of how many species exist in an area or something like this. But sometimes there are multiple species, quadrupeds a lot of times, and it would also help in many cases to know where they are looking at and so on. And what I would like to know is, what do you think would be the bottlenecks in deployment? Is it lack of data sets or accessibility? Like, for example, what Mathis did like with the deep lab cut, that it made it really accessible. So how do you think to go ahead in using these methods and deploying them actually in the data?
Yeah, so so it took us a bit of an effort for learning the model from the toys. And so that's the reason why I recently tried to create these models only using meshes that I could find online. And so the tiger is an example. So, and then I created models for a turtle and fish and a panda. And then I realized that those were sufficient for trying to capture 3D. And so if I had the knowledge, the passion, and I don't know, the technical expertise of Mackenzie, maybe I could create a tool that would allow anybody to convert a mesh into a deformable shape model that could capture shape variation across the single spaces. And I think that would be maybe something interesting to do. Yeah.
Yeah, thanks a lot. There's another question by Mark. You want to follow up?
Hi, that was an amazing talk, and your work has definitely been an inspiration for us. I wanted to ask, so the parameterized mesh models, they have these skinning weights that are sort of telling where the surface vertices go based on the bones or joints. And I'm wondering if you thought about how to, and these are usually artist defined. And I'm wondering if you thought about how to maybe use some texture regularization or some sort of supervision so that the mesh surface points go to where they actually do go on the animal when the animal articulates.
Yeah, that's a great question. And I have a list of things that I was, so as in 2017, we had a to-do list, and this of the skinny weights was one of the entries. And at that time with Michael, we bought this amazing data set that we have with all these videos, high resolution videos of animals without any occlusion. And that is the perfect data for learning how the skin deforms with motion. Because yeah, like if you can get this type of data where you have wild animals without occluded paws and without tree shades and like in control viewing conditions and without any occlusion, then you can really learn something interesting about how they deform. Yeah, we still have to do it.
That's great, thank you. Yeah, I'm super interested.
It's good to still have open problems for the whole community. I want to relay one more question we have, and then we move on to the next presentation. And there was a question by Li Hang, what the input to the small model is. And I think you presented lots of different techniques, like one were just on the body models, others also integrated neural networks to estimate the body parameters. So generally, what's the input you need and for training the models and also at inference time? I guess it's best if you pick one or two of your works and explain what the input is. One concrete example would be helpful.
So, so for the zebra, I don't know if I understood correctly the question.
I think it's at inference. I think they wanted to know at inference time. Do you have to? Is a manual mask required? Are key points required?
Yeah, yeah. So for the dogs, we just have a picture as input, and actually we saw it works even if you have like a tiny dog or a big one. So we do this RGB to 3D prediction without key points or segmentation masks at test time. So in the network works, and in the optimization works, we have the key points and the segmentation mask, but that is a completely different approach. It's not based on a lot of data. We just optimize for some few images.
Okay, yeah, thanks for clarifying, Sylvia. And thanks again for your talk, impressive work. I had actually a couple of questions and you answered them, a lot of them already during the talk, so great. Thanks again for this. Yeah, in the spite of time, let's move on to the next presentation we have. And this one is on tracking grow finish pigs across large pens using multiple cameras. Lots of words I don't know as a computer scientist. What are grow fish pigs? Looking forward to hearing more about this. This is a presentation by Yongjong Lee from the University of Illinois and a couple of other researchers there. You have it on the slide. Please go ahead.
Hello everyone, this is Aniket Shirke from the University of Illinois at Urbana-Champaign. And today I'll be presenting our work tracking grow finish pigs across large pens using multiple cameras. Pigs are one of the most commonly raised livestock animals in the world, and they form a primary protein source. To cater this need, it is imperative to improve the efficiency of livestock systems. For efficient pig production, we need to monitor the health of pigs, and as a first step, it could be best done by tracking them accurately in farm environments. There has been progress in monitoring pigs in real time using single-view cameras, where pigs are detected and tracked by deep learning methods such as single-shot detectors and correlation filters, or key point detection networks. Unfortunately, these methods fail when the pen size increases. Due to the large pen sizes at commercial farms, a single fixed camera does not cover long pens at adequate resolution. Hence, there's a need to have multiple cameras to monitor pigs housed in large pens. In order to track animals across multiple camera views, we develop a homography-based multi-camera tracking system. We also provide a fully annotated multi-camera, multi-pen pig dataset. In order to tackle the problem, we first placed 3 RGB cameras which monitored 2 pens in such a way that the drinkers and feeders of both pens were visible from an angled and a ceiling view. In our inference pipeline, we first detect pigs using state-of-the-art object detection model, YOLO V4, and assign each pig a local ID in a single view using an object tracking algorithm, deep sort. We then combine the local IDs coming from different cameras using the homography between different camera views to achieve global tracking. Specifically, the bounding box from the ceiling views can be considered as a quadrilateral on the pen floor in which a pig is enclosed. We project this quadrilateral from the ceiling view to the angled view using the homography between the two views. The bounding box from the angled view is then matched with the projected box from the ceiling view, thereby achieving global identification. Coming to the evaluation of our approach, we annotate 429 images in order to train the YOLO V4 model. To evaluate the efficacy of our system, we build a validation set by annotating every 15th frame of 5 2-minute-long video sequences. We achieve a multi-object tracking accuracy of 65%, and a multi-object tracking precision of 54.3% for tracking pigs locally using deep sort. To evaluate global tracking, we report the ID handover accuracy, which is defined to be the fraction of identity matches for the 2 views predicted by our algorithm out of the total ground truth matches. We achieve a handover accuracy of 74%. The results can be improved by addressing the several challenges faced by the model. As pigs tend to huddle to maintain the warmth of their group, some pigs are occluded or counted twice, leading to false positives and false negatives. Moreover, due to rapid social interaction in the huddle, the identities of pigs get swapped, which is not rectified by the appearance model of deep sort. To achieve global tracking based on homography, there is also a need to maintain tight synchronization between multiple views. In conclusion, in this work, we address the problem of tracking pigs in large pens by developing a homography-based multi-camera tracking system. We also open source a fully annotated multi-camera, multi-pen pig dataset, which can be used by the community to develop deep learning models. Our code can be found at the link provided in this slide. Thank you.
Yeah, thanks a lot. Great presentation, really solid system integrating classical computer vision with homographies. Do we have a pressing question? Otherwise, I would, in spite of time, move straight to Andrew's talk and then have the Q&A together after the session, at the end of the session. I don't see any hand up. So Andrew, please prepare your screen. In the meantime, I will introduce you. So yeah, Andrew Fitzgibbon is very well known. He has more than 10 Best Paper Awards at various conferences, top venues. He's also a fellow of the UK Royal Academy of Engineering. And yeah, so a superstar. And worthwhile noting 3 contributions he has done. In 2000, he created the Emmy Award-winning 3D camera tracker Boyu. Of course, not single-handed, but he had a significant contribution there. And then in 2009, he was part of the Kinect team, which you all might know from your game consoles, but it played a huge role in research, enabling lots of work in computer vision and also for animals. And then, yeah, in 2019, you might know him from his efforts in HoloLens. His team was responsible for the articulated hand tracking in there. Personally, one of the first papers I read from Andrew was actually his papers on a paper on dolphin tracking. What shapes are dolphins? We've already seen the picture in the intro by Michael. So quite influential for my own career. Thanks for the great work. And I'm looking forward to what you're going to present to us today. So please, Andrew, take the stage.
Thank you, Helga. That's a very kind introduction. Can you hear me okay?
It's all good, yeah, clear.
And can you see my mouse?
Yeah.
If I point at stuff.
It's relatively small, but we see it, yes?
Yeah, I won't try to do anything special. And I will speak for 28 minutes. Is that fine?
That's perfect, yeah.
Yeah, good. Okay. So welcome. Thank you very much for inviting me. When I thought about this talk, I had been watching a TV series called The Durrells, which is great fun, and I recommend it to you. And I thought there was a book called Humans and Other Animals by Gerald Durrell. It turns out there isn't, but there are loads of books called Humans and Other Animals. And why is this title so popular? Well, I think it's one of the reasons is that humans are quite similar to other animals and quite different. And in a computer vision point of view, it's worth, humans are interesting because it's worth annotating a lot of human data. Animals vary so much that annotating animal data means we have to use cleverer techniques, I think, sometimes than we can apply to humans. But let me sort of do a little sort of brief history, right? First of all, you mentioned that I was working on the HoloLens, and I just want to sort of remind you, it's this head-mounted device. You put it on your head. And Julia Schwartz here, who's sort of the engineer and designer on the hand tracking, is showing how a tiny device here, a 500 megahertz processor, 2 processors, can allow us in real time to get a fully articulated tracking of the human hand. So what are the technologies that we can use to do that in real time, really fast? And I'll talk quite a bit about deep learning, model fitting, etc. But before that, let me just sort of go through, I took the opportunity to look at the animal work I happen to have done over the years. It was done with a range of collaborators. The resolution of the image gives you an idea how long I've been working with the person, because the image has obviously been copied from slide to slide. I need to fix that. Jamie, Jonathan, Mukta, Tom, and recently Ben Biggs. Ben is in the audience. Ben, can you wave? It's been kind of fun, and you know, I'm definitely a form of imposter here, because all I really care about is fitting 3D models to data. And animals were good, interesting, difficult ways to try that out. So I looked back, and yeah, I'd been using giraffe since 2004, but one of the first giraffe papers was this one with Pushmeat, where we tried to upgrade homography techniques to work on curved surfaces. And then with Mukta, we tried to look at things without point correspondences. Then with Tom, can we do stuff with smooth surfaces? That turns into hand tracking, and I'll show you a little bit about that. And then when Ben arrived, we actually got back to doing animals for animals' sake. And I'll talk a little bit about Ben's two papers, Creatures Great and Small, and who left the dogs out. And Michael, I think you forgot to mention that one of the joys of working in this field is that we get to do fun titles again, which is something that we used to do in the 80s, and this field has been working hard on. So I'm just going to tell you a little bit about these old papers, because I think it's sort of fun, and this is probably this is one of my favorite papers I ever did. It's not actually very useful, but I really like the idea. So what did we decide? We decided, wouldn't it be great if I could find a single unified representation of this video sequence? And for the background, we knew exactly how you do it. You compute a homography and sort of lay out a flat texture map of everything that happened in the sequence. What do you do for a deforming object? And you know, what I wanted was a deforming object that deformed a bit, but not too much. So can I extract the sort of simultaneous texture map of the forward-looking giraffe and the sideward-walking giraffe? And why would I do that? Well, we didn't really know, but we thought it would be good that you could maybe stick a logo on the object. And that would illustrate that you had understood something about the 3D shape without actually doing 3D shape. So that was all very well, but computer vision is actually really easy when you've got these high contrast features. And one of the things we wanted to do was get away from that. But of course, I also want to remind us that we tried it on animals and then hoped that would work on humans. And again, you get to do the same creepy thing on this poor human. So you paint on the texture map and then replay that through the video to give it sort of some creepy eyes. Again, no real use for that, but made us think we were making progress. So the question I wanted to ask then is, oh, okay, but point tracking makes it super easy. You know, what would I do, computer vision without point tracking? And you know, the answer was none. I thought, what's an object that's nice and simple, but curvy and bendy and doesn't have points on it, but maybe has edges? So of course we search for clownfish, and we say, can we build a 3D model of this class? So this is work with Mukta Prasad and Andres Zisserman in 2010. And, you know, we worked hard and we did things in coordinate systems. Oh, sorry for the layout. And eventually found that we could make ourselves sort of reasonable looking 3D models of clownfish, which, you know, it's important to have a table with those guys, boo, and us guys, yay. So we generated such videos. And you know, again, this isn't supposed to be useful in itself, but the idea is, are we making progress towards understanding how to pull out 3D shapes of more and more constrained or less and less well constrained scenarios? So again, boo, yay. I don't really believe in tables of bold numbers, but I'm assured they're very important. So then we thought, okay, edges was kind of cheating, because really they're just like, you know, points are 0D and edges are 1D. Can we really do it with nothing? And then, of course, what's an easy-ish shape that has no distinguishing or not very many texture features? And the answer is dolphins. So could we get a collection of dolphins and figure out somehow what the 3D underlying shape is? Answer, you know, spoiler alert, kind of no, kind of yes. So what do we say? Well, what we're going to do is it's easy enough to segment them. So we'll assume we've segmented the dolphins. it's silly to say there are no feature points. There are some feature points, right? So, you know, on each dolphin, there may be 5 feature points that you could click manually. So we say that's okay, you're allowed to use those. But the real trick is, can we use the silhouette? And Sylvia was saying, you know, the silhouette has some information and not a lot. It's true, it doesn't have a lot. But here we were just trying to figure out, you know, what information can I get from the silhouette? Is there anything, you know, I can learn? So silhouette plus point features. This is the boo, because, you know, we had to kind of tell it what it was before we did it. But really, our argument is it's pretty easy to make a dolphin template. The hard thing is to match it to the images and learn about movements. So we were pleased with ourselves because, you know, we managed to get this thing that would automatically discover the sliders and would sort of play through the dolphin. Now, remember, there's no skeleton in here. Why? Because despite the name, it's actually not that simple to write the code to do full linear blend skinning. And I like the way we've sort of evolved over the years. Our models get more and more complicated as one group says, hey, it's not that bad, and everybody else can kind of dive in. So we all helped ourselves, I think, to build these models. And then the evolution from clownfish to dolphins was that we could, with a depth camera on a relatively low-powered machine, Surface Pro of that era is about 25 watts, we could build a hand tracker that allows us to interact with a 3D world. So I think what's nice about this is that almost exactly the same code that was used for dolphins was used for the hand tracker. Now, this one does have a skeleton, so inside the hand, so we had to do extra code to do the linear blend skinning and so on. But lots and lots of the code was reused from dolphins to hand tracking. And I love this bit when his finger touches the slider. That's the point when you realize you're not going to need haptic feedback for this. And I don't know if anyone's used the HoloLens hand tracker, but I don't know. I think you don't need haptic feedback today. So there we go. So, you know, how does the HoloLens hand tracker work? Well, here are the raw images points from the depth sensor. Here's the model in every frame being fit to the raw data. And just to really hammer it home, right? These are like, I don't know, 5, 6, 7 iterations of Levenberg-Marquardt, connecting the raw sensor point in red to simultaneously inferred surface correspondences in blue. So, you know, the story is here, you can use model fitting with Jacobians and Levenberg-Marquardt in real time. It works fine, okay? So then the obvious question you need to ask yourself is, right, Andrew, you've done it without points, without lines, without, you know, with just silhouettes. Can you get over your obsession with model fitting? And this is a very pertinent question, I think. Oh, but a problem happened, right? My brain segmentation faulted when I was asked to do it without model fitting. And the reason this is pertinent is, of course, it reminds us of this recent question that was raised by our esteemed colleague. What did senior computer vision people like me do when deep learning came along? And I thought about that and I thought, yes, I definitely recognized various stages of concern, which reminds me, don't answer it now, but I think there's another one about technology adoption, where one of the punchlines is, oh yeah, it turns out I was doing that all along. So if anyone remembers that, pop it in the chat. And what I wanted to get here, and I think this is the message that we're beginning to learn for ourselves, is that actually the key message of the talk is, yes, of course you should use machine learning or deep learning, right? Because it's stupid to use model fitting, you know, with 100 random starting points to try and fit some data that wasn't even from the model anyway. And of course, you should use model fitting, because once deep learning has got you close, or machine learning has got you close, it's kind of silly to use the excess, you know, to 10x the network capacity to get a couple of X millimeters of accuracy. And the other advantage of model fitting is not just that it kind of gets you the last mile very quickly. The joy of model fitting is that when the user sees it go wrong, so I'm waving my hand here, and the HoloLens thinks that my hand is one finger to the left, the user can understand. It's perfectly explainable. It's, oh, silly HoloLens, you know, it doesn't notice that my little finger is down, it's made a mistake. Maybe I should just wave my hands at it and get it to reset. So there's something nice about model fitting where the user can debug easily what's happened. And of course, if the user can debug it, then we can talk about explainability and we can talk about where we got our likelihoods and so on. So there are other advantages. I don't know which stage this is, Michael. I still may be in the bargaining stage, but you know, this is the way I build systems today. Yeah. Now, and then I thought, actually, it's funny because the story we used to always tell about Connect was, if you remember, you know, 10 years ago, image in, pure machine learning, centroids of the joints, and you know, you watch the left hand carefully, and as the hands move around, the left hand should stay orange, even if it's over on the right hand side of the image. So, you know, pure machine learning can give you the joint angles. It's funny because this system, first of all, two things. Number one, is not pure machine learning because there is actually a stage after it to do with tidying up the joints, which I'll tell you about. But funnily enough, this system was actually built on top of this system. And I don't think lots of people have seen this video. This was a sort of internal first iteration when we told the Xbox people it was impossible to do body tracking. And they showed us that they had built this system where if you started in the right, you know, sort of T-pose, that it would track you through the sequence. So it was funny because it was a model fitting system that wasn't working. How was it not working? It wasn't working because, oh, sorry, I'm missing the frame, but you can probably imagine why it wasn't working, because it works fine for about 10 seconds and then it collapses. So we built a machine learning system to realize reinitialize the model fitter. The machine learning worked so well that we were going to just use it. And then at the very end, I don't think I've ever told you before, there's another little model fitter on top of it inside the first Connect. So that's great. Cool. Okay, so that brings us roughly up to the present day. How should you build systems? You should use a bit of both. I still think that's probably true. And we'll see that in pipelines. We see that in pipelines, particularly in this workshop as well. I think we see these kind of deep learning in and then differentiable render or classical render or whatever to explain the data. So that's really cool. So let me talk a little bit about Ben's paper. I'm going to get it completely wrong, Ben. So, you know, feel free to interject and correct me when I do wrong things. And this is the work that we did, you know, a couple of years ago, which I think was sort of an interesting question that Sylvia again refers to, which is, okay, for things like HoloLens hands and for things like Connect, what do you do? Well, you know, you go to a Hollywood studio and you get them to build you, you know, 1 million synthetic training images. And that's not easy because A, we had lots of money. It's easy because A, people already in the games industry or in Hollywood have done lots of work on modeling humans. So we're able to leverage that because humans are easy to build synthetic data for. But we don't have that in animals. We just, you know, there isn't even that much expertise, I would say, in building synthetic animals. And of course, for Connect, we were simulating data from a camera, from a depth camera, and simulating from a depth camera is so much easier than simulating from an RGB camera. So when Ben came, Ben, you know, really wanted to look at animals, and the natural thing, you can't really have a range sensor looking at horses in a field. You can't even have a, you know, you don't even know how the range sensors are going to interact with animals in some way. So we want to use RGB data, and we want to use kind of across animals, across breeds. So there's a rarity of data. So we tried a few things. We tried to, you know, do the sensible thing, right? Do the 3D Safari thing and gather good synthetic images, realistic backgrounds. And to be quite honest, you know, it's a lot of work. So we kind of decided we would try to bypass that. Ben's done some nice work on, you know, using a GAN to generate, to go from a kind of Vitruvian manifold to you know, to a more realistic sequence. But again, that was a bit tricky to get work, and we got to work in a human 3.6. So one of the things we thought is, well, simulating RGB is really hard. Simulating silhouettes should be easy. Can we overcome the difficulties of not having lots of data by just generating loads and loads of silhouettes from SMAL, and then transform our input image to a silhouette and then match at that level? And I think that was quite successful, and I think that's, you know, quite pleased with that. I'm going to just point to a few sort of highlights of the work that I like. One of the things that Ben was doing was you know, a sort of classical, let's say, deep learning predictor, given the silhouette, can I predict the position of certain well-known joints? Because we have synthetic data, we've got great training data for where the joints are. But of course, you can't get past me without doing some energy minimization. So, or some model fitting. So if we look at the raw network predictions here, you can see some classic sorts of errors that systems will make, right? As somebody earlier mentioned, left-right errors. I'm not going to claim we're going to solve those with silhouettes, but you see just general errors of swapping predictions onto the wrong parts of joints. You know, in this case, the raw network predictions are quite good on the head. Then, but of course, we were predicting these on video. So you can add some terms. We added a term which is make it temporally coherent, and another term which says, please try to make sure that the skeleton is covered. And it's quite interesting trying to set that up. So there was a thing with a medial axis transform and a thing with some silhouettes and some alpha shapes. So, you know, I encourage you to look for L-Skell in the paper and see what tricks you use to try to force all pieces of the skeleton to have a prediction. And then the final thing you want to do is to penalize what's happening here, which is a bone is passing over free space. So again, you know, it's easy to imagine how you would write a, you know, some renderer that would penalize bone going over free space. But how do you do it in such a way that you can solve it using a quadratic program or some simple solver? And again, that's what's solved in the paper. I think it's great. And then, so again, we see, you know, kind of jittery, often wrong prediction coming out of the network is processed, first of all, temporally coherent, so a little less jittery, but still with the flicking backwards and forwards across the legs. And then finally, when you impose the skeleton term, the non-falling into free space term, and the and temporal coherence, you get, you know, a better prediction, which and there is a table of numbers, and ours is in bold, so it must be good. Cool. Okay, and then, you know, what do you use the points for? Well, we'll do a little more model fitting. So this is just reminding you what it looks like to fit a small model to a single silhouette. I never get tired of watching 3D models fit to things. So that's an example of the kind of reconstruction you would expect from one frame. And then, of course, when we do it coherently over time, then, you know, what you want to get is this nice animation of you know, dog on beach. As you can see from this viewpoint, you know, if you know, the dog is more lavish and this is maybe more Alsatian-ish, but, you know, we've gone a long way in 10 years, I think, in how well we can process these videos. And then again, we can see, because this work is applies to, you know, all the animals in the SMAL menagerie or repertoire, then again we can do tracking from, this is the Davis video segmentation data set. So we have access to silhouettes, you know, sort of state-of-the-art silhouettes, because people are competing on that, or ground truth silhouettes. And we can see that we're getting decent tracking here. So that was, you know, I like that. I like this this way of post-processing your point predictions, which is not necessarily differentiable, but I think you can insert it in the loop. Actually, it might be differentiable, Ben. We should check, or if we, yeah. And then let me talk a little bit about the recent work where we called "Who Left the Dogs Out," where I bet somebody else in the audience had the same title at the same time. The observation here was, for all the work we were doing, we weren't dealing with the animal, of which there are 41 million, you know, domestically owned in the US. And I don't know how much people spend on their dogs, but they must spend like $500 or $1,000 a year on their dogs. So, you know, this sort of super important category, almost as important as humans. And we were wondering, well, you know, and again, it's been referred to earlier today, why would we not do dogs? And the answer is, I guess, two things. Number one, there's actually quite a lot of variation on dogs. I presume it's because of domestication and people kind of fiddling with them. I mean, breeding. So there's lots of different, you know, lots of variety in the appearances of dogs. And I guess because dogs interact with humans a lot, there's maybe a lot more variety in the kind of environments in which you find dogs compared to, say, cows or elephants or giraffes. So dogs were interesting and hard, we thought. worthy of investigation. So I won't go through, the paper in total. I'll pick a couple of highlights that I like. But roughly speaking, so we want to solve the problem of picture in, 3D dog model out. We want to do it again, using reasonably weak supervision, using the Stanford Extra, the now lovely Stanford Extra database. One of the things we did was enhanced SMAL a little bit. So we've got a kind of a dog specific 3D dog model, which, is good for dogs, and we recommend it to you, and you should try it for other things as well, or, you should try expanding it. And then there's a kind of a cool idea here where the SMAL shape prior obviously is over a big range of animals. Even if you restrict it to the space of dogs, there's a lot of variation. And when you're doing a given sequence or a given image, it's nice to be able to just sort of refine the Gaussians or the mixture of Gaussians so that you have a tighter prior over the particular image or images you're looking at. So that's a nice component. What does who let the dogs out architecture look like? Well, it's the classic, bit of deep learning, predict camera pose and animal pose and shape, pass them through a renderer, compare to image, return answer. So, I like this architecture. I think it's great. And then when we're training, there are a couple of extra losses where we're also simultaneously optimizing over the shape prior, which I know technically doesn't become a prior anymore, but means that we now have much better predictions. And then we can compare through the differentiable renderer joints and silhouettes, giving us decent results. And of course, in both of those papers, and this is not the only work Ben's been doing, but in both of those papers, we get these splendid data sets. So it's been mentioned earlier that we've got Badger with handy joint annotations. And of course, there is Stanford Extra dogs, which again has been mentioned. So, we should all thank Ben and colleagues for the great work on assembling that. Mackenzie's giving you a round of applause. So I'm finishing a little bit early, but that's fine. So what's my key message is, yes, use both, right? Machine learning is great, model fitting is great, and we should all be friends. Thank you very much.
Thank you, Andrew. As always, a pleasure to listen to your talks, and good to know that there's still some model fitting, even the first Kinect. Do we have questions from the audience? So maybe for the procedure of the day, until people, I see there's one already. We'll have a poster session afterwards. I will give you a short intro how this Scholarly works. I'm new to this as well, so maybe we can do that together for those who are new and experienced. Yeah. So, but first of all, so we have QI, then the poster session, then another 2 sessions, and again for everybody who has still energy afterwards, we open the poster session again, so you can go back to this. But first of all, yeah, let's come back to Andrew's talk and also the presentation we had on pigs, as well as Sylvia's talk on animal models. So I see Michael has a question.
Well, yeah, so since you mentioned with the Connect that you actually did fitting, you also said that you were evaluating this billions of times a second. Did you really do billions of fittings a second?
No. That was, I was misquoted. We were trying to say that if you did exhaustive search over human pose space, that would be billions of poses. Because I think we were doing, 10 to the power of 13 was, joints. Yeah.
Well, so
no.
So
the fitting was the fitting was actually very like, or not very like, but a little bit like Ben's coherency terms on the 2D predictions. So we just had a bunch of those.
Okay. So on your way from your state of bargaining to full acceptance, you could have your cake and eat it too by doing the trick that Sylvia did, which is optimizing with the actual network itself.
You mean in the loop?
Yeah, well, she did it post hoc and SMALR to optimize. I mean, the network is like a great big objective function that you can optimize. Okay.
Yes.
Maybe
Ben, do you
Sylvia
want to
can
tell us a
comment
bit
on
more
it.
about how that, this skinning is hard-coded, I understand. Are there any parameters in the renderer?
No, not in the render. I think, Michael, are you getting to the idea of running an energy minimizer, but using the sort of network weights as free variables, so you can kind of optimize
exactly.
per image.
Tune
Yeah,
them,
it's a really nice idea that we've not looked at specifically, but probably should.
Thank you, Ben. Thank you, Michael.
There's another question from Maxine.
Yeah, hi. Thanks, Andrew, for that amazing talk. That was a bunch of fun too, and an amazing historical context. So thanks for all your incredible work, for sure. So yeah, maybe just for the larger crowd of you and Sylvia and Ben, feel free to chip in too. I wonder your experiences with like blobby animals, right? Like for example, rodents are just these like furless little featureless creatures in many ways. And so maybe with the dog work, I'm just wondering, like you mentioned, like the species can be so different. And there's just, there's these like very blobby dogs and then very lean dogs, like a greyhound. And like, how do you see kind of optimizations in that space going?
I will definitely defer you to Ben for rodents.
Yeah, it's a really interesting question that, to be honest, I've been thinking about a lot to do with the the sponsorship for my PhD. Like it's definitely true that the silhouette term can help a lot in terms of encouraging good shape alignment, but I think there is a kind of more general question, which is how to scale up some of these techniques that involve 3D morphable models to larger animal categories. Like when we're talking about rodents or maybe like an octopus or something, is it the right strategy to design a specific template for every single one of these species? The answer could be yes, but maybe otherwise we can look at some of the recent work in implicit functions, or a lot of stuff's going on with NERF at the moment, particularly like articulated NERF. I think Michael has a paper or something in humans, but also kind of learning more intelligent training networks to represent spaces, shape spaces, is like I think a really interesting direction. But yeah, if you want to do something with rodents, I'd be definitely keen.
Cool, Ben. Thanks. Yeah, thanks for your great answer. It's awesome.
But Ben, you've also done like actual explicit rodent tracking, right? Completely old school, but you've really worked on them.
Yeah, that's right. So there's a good open source data set with rodents and annotated behaviors. It's the SCORE. It's SCORHE, I think. It's by the National Institute of Health, the US group, and that's really interesting. So you can just do something really simple and train a classifier on images and predict behaviors. And I've recently extended that to sort of multi-housed dogs. They're supposed to be kind of together for good, welfare reasons, but yeah, you can put sort of pose predictors and behavior predictors on top of RCNN heads and things, backbones to do things in that space. So
yeah, super cool. Yeah, thanks for your perspective, both of you.
Awesome. Yeah, thanks for all your comments, questions, discussions. It's amazing. I really enjoyed this workshop. There's more to come. Let's thank all the speakers of this session again. And I would also like to give a shout out to Hyung-Soo Park. He is really the main organizer of this workshop. He did the main legwork, and it has come out really well. Thanks to all your work. So with that, essentially we're gonna open the poster session. It's like a normal physical poster session where you walk around. There's nobody of us guiding you. You're free to roam. It's up to you to engage. It takes a bit of a barrier, but we encourage you to walk around, go from poster to poster, either roam around randomly or look at our website. Maybe somebody can post it in chat, or I manage as well. So you can see all the posters there with ID, and the ID you see on our webpage is the same as the poster ID. But yeah, you're free to roam just around. As Michael said, this community is still small enough so you can talk to everybody. Let me share my screen and walk you through the Gather session. If you're familiar with the session, feel free to already go there and engage. Otherwise, I will just do a little bit of a walkthrough. You should be able to see my screen. And we can give you a direct link to a Gatherly. It's the following. So when you click on this link, I will do it now. It opens the Gallery webpage. The first thing you will have to do is to enable the camera. I already did that. There will be a small pop-up asking the browser asking you to give this web page permission to see your camera and so on. You have to do that. So I will just select here some default ones, microphone. Make sure you select the right one. I have a couple for choice. So you have to go through that. There's also a small tutorial. You might be able to skip this if you now follow this one. So close the session here. And I think you should already see a video of yourself. For me, it's now still on Zoom. That's why you don't see it. So let me explain the layout here a bit. On the top, this is like a real conference room. You can walk around by just clicking. So I'm here. I was here on the top. You can walk around in the room. On the top is a welcome. And you want to go to the elevators to find the right poster session. We have 3 rooms for CV4Animals. Poster 1 to 20, 21 to 40, 41 to 51. So I don't expect anyone in the 60s, but last paper is, I believe, 51. And yeah, maybe choose a random one here, not just all go to number 1 to 20. Let me go to this one. So I'm now moved to the elevator just by clicking on my screen and move to that room. Now you can see all the posters. And yeah, somehow you have to close this highlight again, but then you can move to a poster. If there's nobody around, nothing will happen. But as soon as you get close to somebody, let me pick this poster, the chat will open, and you will also have the option here to share screen. So for the presenters, we expect you to share the screen to bring up your poster or whatever other material you want to show. You could show again a video, and yeah, just engage as with a normal poster with everybody who is close. So in this room, you will only be able to interact with the people right next to you. If you want privacy, you could just walk out and then decide where you want to move next. There's also the possibility to raise a hand, a bit like in Zoom. And your video should start up right away when you come close to somebody. Though there was a question in chat that this screen share functionality, it only opens up when somebody is close. So essentially, whenever 2 or more people come together, a room will be created, and then you can do the screen sharing. Anything else I should mention? There's also a chat functionality here, I believe. So you can chat here again, advertise your poster if you're free and looking for customers, then shout out at the event. And yeah, I believe that's it. Let me see if there's any questions on the chat. But I'm also a first-time user, so if you have any suggestions on how better using this, clicking here will move you around. The elevator brings you to the different rooms, and otherwise just click on the poster if you want to interact. And yes, I posted the link here in the chat, so it should be a single click bringing you to this Gallery interface. You select your name and yeah, enable the video and audio, and then you should be ready to go.
Yeah, and also I'd like to mention that the session 3 start at 3 p.m. Pacific. So yeah, please make sure you come on time.
So that's in 45 minutes.
Yep.
And is that back on the Zoom?
Yeah, it's going to.
So only the poster session will and this coffee break will be on Gallery. We come back to the Zoom, and then afterwards we open the Gallery again, or it's open anyways, but whoever has still energy is welcome to go back to the posters. Okay, great. See you all at the poster session. Looking forward to learning more about your work. I will stick a bit around here. If you have any questions, if you have trouble joining Gallery, let me know. I will stay around here a bit. Looks like everybody's happy. I believe you will have to, you might want to close Zoom before you go into the Gallery, so your camera is no longer active in Zoom because it will only be able to be shared with one of the machines. List of titles for the posters. Yeah, that's on the paper page. I don't think it's on the Gallery platform. Unfortunately, it's a little limited. But if you go to that link, you can find the list of papers. And the ID will correspond to the poster ID.
Helge, you can start recording.
Oh yeah, I'll look up this.
We're gonna edit the video anyway, but we don't have to record now.
Stop to share.